So our one module this year is matrices. So we've got two chapters, 11 and 12. I'm going to review both of them today. Matrices is still fresh in your mind, so I'm going to go through this one reasonably quickly. Okay, so if you've got any questions, if there's stuff you're not sure of, just come back and ask me about it if I skip over anything that's really obvious, okay, that you need help on. So and that could be the case, but we're going to go through this reasonably quickly because it's still pretty fresh in your mind. So a matrix is just a table of numbers. Have rows, has columns. Okay, the order of the matrix is the number of rows. So the number of rows, 1, 2, 3, 4, 5, 6, 7, 8 rows and 4 columns. So the order of this matrix is an 8 by 4 matrix. Okay, 8 rows, 4 columns, order of the matrix. So that means it's got 32 cells. And what we can do with a matrix is we can transpose a matrix. Okay, and the little symbol uses this little T, so we can transpose a matrix, and that means the first column becomes the first row. The first row becomes the first column. The second row becomes the second column. The third row becomes the third column. So it's transposing a matrix. Okay, so and we use this little T symbol, and there's a particular way of doing it. You have to go through the menus to do it on your CAS. Make sure you're aware of how to actually go about that on your CAS and do it through the menus. Okay, so it's, you've got a matrix there and you just go menu and there's a matrices tab and there's one that says transpose. And little T will appear, you can hit enter and it will transpose the matrix for you. Then you can store it as a different matrix. Okay. So a few little things. Identity matrices is basically like the number 1. They've got ones down the now let's say down the left to right diagonal. Okay, all ones down the left to right diagonal, zeros everywhere else. Okay, so what happens, say we've got this matrix B, a 3 by 3 matrix B, and we multiply it by a 3 by 3 identity matrix, which is I. Well, B times I is B. I times B is B. Either way, you're going to get the same answer. Okay, that's what the effect of the identity matrix. It's like multiplying by the number 1. Okay, and in a matrix, we can pick out any cell. The cells, always when we're referring to matrices, the rows are first, the columns second. Just keep that in mind. Rows first, columns second. So when we have, say, L2, 3, it's row 2, column 3. So row 2, column 3, and we get that cell. So up in this matrix up here, if we want B1, 2, it's row 1, column 2, row 1, column 2, and we've got that 7. B3, 1 is row 3, column 1, and we've got that 3. Okay, so on page 371, there's a little bit of stuff about CAS. It tells you how you need to go about transposing a matrix, also about how to enter a matrix. 2 by 2 and the 2 by 1s and 1 by 2s are really easy to enter. If you want, you need to be able to enter any size matrix. Okay, so make sure you pause the video, have a look at page 371 and just refresh your memory with how matrices work, and I'll see you on the other side. Okay, so what we're going to look at here is just representing information with a matrix. So I've skipped over the bit about representing a table because that's just pretty much copying the table into the matrix. What we are going to look at is representing a network diagram. Okay, so in this network diagram, we assume you can go either way. There's no arrows on here, so we can go from 1 to 2 and from 1 to 4. So we can go from 1 to 2. So first of all, there's no loop, so you can't go from 1 to 1 or from 2 to 2 or from 3 to 3 or from 4 to 4. We can go from 1 to 2 and we can go from 1 to 4. We can't go from 1 to 3, so it's a 0. From 2, we can go to 1, 3 or 4. So from 2 we can go to 1, 3 or 4. From 3 we can only go to 2. So from 3 we can't go to 1, we can go to 2, we can't go to 4. And from 4 we can go to 1 or 2 but not to 3. So from 4 we can go from 1 to 2 but not to 3. And we'll see we've ended up with a symmetric matrix here. Okay, so that's just using a network diagram to represent a matrix. There's another example you can have a look at if you want to see some more. Example 9 on page 376. Pause if you want to have a look at it, and then I'll see you over the page. Okay, adding and subtracting matrices is really straightforward. They have to have the same order. Okay, so this is a 2 by 3. This one's a 2 by 3. Because they've got the same order, we can add them. We just add the cells. 2 plus 1 is 3. 3 plus 2 is 5. That's it. That's all there is. Subtracting will be the same. We'll just go, if we're doing A minus B, we'll go 2 minus 1 is 1. 3 minus 2 is 1. 0 minus 3 is negative 3. Okay, so that's straightforward. We can always also do what's called this scalar multiplication. So we're just multiplying this whole matrix by 3. It means every cell gets multiplied by 3. So 2 times 3 is 6, 3 times 3 is 9. Okay, so every one of these numbers is 3 times the corresponding number in this matrix. They're reasonably straightforward. There are some more examples, 10, 11 and 12 on pages 379, 80, 81, if you want to see some more of that. But this is the key one, is multiplication. This is important. You need to know how this works. Yes, your CAS calculator will multiply for you, but you need to know, as you found out on the SAC, there's a question on the SAC where people had to say how a particular value was, what the calculation was. Not very many people got that mark. Okay, so you need to know what's going on. So first of all, we need to be able to determine if a matrix can be multiplied. What's the word for it? If it's defined. Okay, so this matrix is a 2 by 2. This matrix is a 2 by 1 because the number of columns in the first matrix is equal to the number of rows in the second matrix. It is defined. Okay, if you ever ask that question, don't say that number and that number. Say the number of columns in the first matrix equals the number of rows in the second matrix, so it's defined. And what we end up with is a 2 by 1 matrix. So to get there, the first cell is the first row times the first column. Okay, so we go 11 times 6 plus 5 times 1. Okay, first row by first column, first row and first column. Second row by the first column, so we get 10 times 6 plus 9 times 1 and get 69. Second row and first column. Okay, so if we're going to multiply these two matrices here, we're going 2 by 2, 2 by 1. Yes, it's defined. We're going to get a 2 by 1 matrix, so we're going to get two numbers. So we'll get a number there and a number there inside the matrix. Okay, first one, first number, we're going to go this row with the column. So 1 times 2 is 2, plus 0 times 3 is 0, so our first number is 2. Then we go the second row with the column, second row and first column. 2 times 2 is 4, plus 3 times 3 is 9, so the second value is 13, and that's our value. Yes, you can do it on the CAS. Make sure you know how to do it on the CAS. If you try and do it on the CAS, if we flip these around and did them the other way, then we'd have a 1 there and a 2. Sorry, I can't point to the screen, that's no good. We'd have a 1 there and a 2 there, it wouldn't be defined, and your CAS will give you an error. Okay, so that's matrix multiplication. Okay, so now we're just going to look at to the end of chapter 11, communication matrices. So people communicating with each other, and we have there's two-way communication everywhere, but Eva Wong is the only person to communicate with everyone because of language differences. So Eva can't communicate with Kim, etc. So what we end up with, and just let me get up to where this is. So what we end up with is Eva, so it's going to be zeros down a diagonal again. This is very similar to the one we did before. Eva can communicate with Wong. Well, everyone can communicate with Wong. So we're going to have ones all down Wong, and we're going to have ones here across for Wong. So Wong can communicate with everyone except themselves. Technically you can. But we don't mark that in, that's redundant. Okay, and everywhere else is going to be zeros because no one else can communicate. Eva can't communicate directly with Yumi. Eva can't communicate directly with Kim. So we've got zeros everywhere else, and we end up with this communication matrix, which is this one down here, and we're calling this matrix C. So if we have a look, if we do C squared, and you do it on your CAS, if we do C squared, that gives us all the two-way or two-step communications. So everyone can do a two-step. So except for Wong, with Wong there's no two-step communications because everything is direct. Okay, so there's only one-step communications for Wong. Everyone else, there's 1, 2, 1, 2. 1, 2. Everyone can do a two-step communication, so we get ones in all of these cells, and if we add them, so we get ones in all of these other cells. Okay, and if we add the C and the C squared, we get all the one and two-way communications. So everyone can communicate with everyone else in at least at most two steps, two steps. Okay, and that's what this means. And we'll just have little bit look at dominance. So dominance is a very similar idea to what we've just done, except this relates more to sports and gaming. So we can have, where were they? So Anna has a one-step dominance. So Anna beats Kaz. Okay, Anna beats whoever D is. Okay, so they're the dominances. So they're the one-step dominances. B defeats A, B defeats C, B defeats E. Okay, B doesn't defeat D, but D defeats B. See, so the one means that the person here defeated the person over here. So the one-step dominances, so when we look at the one-step dominances, we see that B and E are equal. So we want to have a look at their two-step dominances to see if one of them comes out on top of the other. So one of them is beating better players that have beaten other better players or not. Okay, and that's basically what it means. So we go D squared gives us a two-step dominances, and we get these values. So B then becomes the dominant player because he's beaten people who have beaten other stronger people. Okay, more often than E has. And once again, when we do this, that is just combining the one and the two-step dominances together, and that makes B the outstanding player in this game, in this situation. Okay, so a little bit on dominances. Go back and have a look at the chapter, read through, look at example 25, which is on page 405, and just have a bit of a look back over that and go through that example. Maybe read through some of the information on pages 403 and 404 as well. Okay, so we're going to look now at chapter 12. So chapter 12 we've moved on to, and this we'll start off with the inverse matrix. Okay, so the inverse matrix is a bit like when we do divides, the opposite of multiply, adds and opposite of subtract. The inverse matrix is the opposite of their matrix A. So if we go A times A1, we end up with the identity matrix. Okay, we end up with an identity matrix. Okay, if we go if it's a 2 by 2, that's what we'd end up with. Okay, now to work out the inverse matrix, we need to work out the determinant. The determinant tells us a bit about the matrix. So the determinant, if we've got a matrix A, B, C, D, then if we go A times D minus B times C, that will give us the determinant. So the determinant is used in finding the inverse. Okay, so if A is A, B, C, D, then its inverse A minus 1 is 1 over the determinant. Okay, that thing there is the determinant. 1 over the determinant. We switch the A and the D and we change the signs on the B and the C. So switch them and we change their signs. Okay, so it's 1 over the determinant of A, D, negative B, negative C, A. Okay, and that rule always applies for a 2 by 2 inverse. Okay, that only works though if the determinant is not equal to 0. Okay, so if the determinant is equal to 0, there is no inverse. Now we're going to have a quick look at simultaneous equations. Okay, so these are an important one. These are, I'll guarantee, I don't know what's on the exam, but I'll guarantee there is a simultaneous equation question on each of the exams. I will guarantee that's pretty much a given. So if we've got these two simultaneous equations, 4x plus 2y equals 5, 3x plus 2y equals 2, we can use the coefficients and make a 2 by 2 matrix, and the xy is a 2 by 1 matrix, and the solution is a 2 by 1 solution matrix. So if we multiplied this out, we get 4x plus 2y equals 5. 3x plus 2y equals 2, and we get back to that situation. So we're going to call this matrix A, this matrix X, and this matrix C. So we've got AX equals C. So what we need to do, we want to find the X matrix on its own. So we need to get rid of the A. So what we're going to do is we're going to go A to the minus 1 times A, and so we're going to multiply out the front, because A to the minus 1 times A is identity matrix, which is equivalent to the number 1. That's why we've got an identity, that's its use. So if we're multiplying at the front, then we have to do the same on this side, A to the minus 1C. You can't do, it has to be this order, the same order. So these two cancel out with the identity, and we get X equals A to the minus 1 times C, and that will give us our solution. Okay, so where were we? Where was that question? Those numbers. So if we did that, here we end up with X equals 3, negative 3.5. So little x is a 3, y is negative 3.5. If you substitute that in, you'll get the right answer. So you're basically doing this on your CAS. You define matrix A on your CAS, define matrix, you don't need matrix X, okay, so you define matrix A on the CAS, you put matrix C on the CAS, and then all you're going to do is go A to the power of minus 1 times C, and that will tell you, give you that solution. Okay, so before we go on though, you need to know there are occasions when this will not work. Okay, and it's because not all square matrices have an inverse. So if the square matrix doesn't have an inverse, that means the determinant equals 0. This is not going to work, and that can happen if the equations are inconsistent. So the graphs are parallel. If we've got two parallel lines, basically what we're doing with simultaneous equation, we're seeing where the lines cross. If we've got two parallel lines, they don't cross. And the other thing is the graphs the equations are dependent, which means they're two of the same line. So they don't cross at a single point. They match up with every point is a match. Okay, so those two situations mean we can't solve there's no solution to the simultaneous equation. And that's what it's saying. There is no solution to that when the determinant equals 0. And it's quite simply when the determinant is 0. Okay, last little bit we could look at is some transition matrices. So we've got a transition diagram here. Car rental firm, one in Bendigo, one in Colac. 80% of cars returned to Bendigo if they're rented in Bendigo and 20% to Colac. And if a car is rented in Colac, 90% go back to Colac and 10% to Bendigo. So I see over time that there's more cars going to Colac and less to Bendigo. So Colac's going to end up with more cars and Bendigo less. So we say from Bendigo to Bendigo is 0.8. Bendigo to Colac, we're looking at the arrows, is so rented in Bendigo, so Bendigo to Colac is 0.2. Okay, Colac to Bendigo is 0.1 to 10%, and Colac to Colac is 0.9 to 90%. So that's how we develop a transition matrix. Reasonably straightforward. So then we're going to we start with a starting point. So we say there's 50 cars in Bendigo and 40 in Colac. And so what we do is we use that transition matrix. So this here was a transition matrix T, and we use that transition matrix to see what's happening over time. So after 1 week, we go S1 is T times S0, the initial solution, and we get that after 1 week there's 44 cars in Bendigo and 46 in Colac. So Colac's going up, Bendigo's going down. So then if we go S2 is T times S1, we find out after 2 weeks there's 40 cars in Bendigo and 50 cars in Colac. Okay, the other way of doing this is S2 equals T squared times S0. Okay, we could do it that way. This one is the recurrence relation. S0's the initial value up here, and Sn plus 1, the next state, equals a transition matrix times the current state. Okay. And we can usually find a steady state solution, which means when it settles down, and we've got the same number of cars in Bendigo and the same in Colac the whole time. So we can see it graphically what's happening. The number of cars in Colac is going up, going up, going up, but it can't keep going up forever and it eventually levels out. Bendigo's going down, 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 but it also eventually levels out, and we end up with 30 in Bendigo and 60 in Colac. So we go S1 equals T times S0. S2 equals T squared times S0. S3 equals T cubed times S0. And we get to S14 equals T to the power of 14 times S0. We're always working with S0 and the same power. S15 equals T to the 15 times S0. And S14 and S15 we see there's no change. It stopped changing. Okay, so there's 30 cars in Bendigo and 60 cars in Colac. Okay, so it's a steady state solution. Okay, so that's chapters 11 and 12, reasonably quickly reviewed. With the rest of today, you can go and do some questions from 11 and 12 reviews, or even, probably even better, to concentrate on the chapter 13 revision chapter and get some of those questions done. I'm sure that most of you didn't get a lot of them done in the lead up to the SAC. Okay, so that's where you're at today. I'm available to help on Teams chat. We have the first practice exam starts on Friday, so let's be prepared for it and have all of the chapter reviews done. Okay, thank you, and I'll catch you next week.